Hello, welcome to part 1 of step 29, all about tangents and secants. So step 29 says I can define and use tangents and secants. This is in your book, chapter 9, sections 5 and 6. So the first thing we're going to talk about, the main sort of idea of this first video, is about tangents. So a tangent is a line that intersects a circle at exactly 1 point. So imagine a line and imagine a circle. If you just barely set, maybe like a baseball on a table, it's only going to be able to touch that table at 1 point, just like a tangent line only just barely scrapes the surface of this circle. So like in this example for circle C, this point right here at A would be the point of tangent C, while line AB would be the tangent line. Okay, so some circles, depending on how the diagram is drawn, will have common tangent lines. Okay, so if we had this first example, we want to look for a line that we could construct that would just barely touch both of these circles one time. Okay, so for this first one, think about if we did it across the bottom, we could draw a line, something like that, and maybe say, okay, well, we're going to establish that maybe that's a point and that's a point that the circles will touch. Okay, similar thinking, we could draw one across the top, something like that. And obviously, I know these aren't going to be exactly perfect, but we'll just show that we can draw 2 there. Okay. B is very similar, but a little different. The 2 circles are just slightly separated from each other. So we could use the same idea that we did in A, and maybe that's one line, and this is the other. Okay, but since they're separated, we could actually draw 2 more. One like this, and the other. Oh, that was not good at all. Maybe something like that. Okay, but a tangent line, like I said, it's just imagine you have a circle. If you cut out a circle on a piece of paper and you just barely laid it onto your hand, where it would only like one little piece of your hand or your finger would touch that circle. So it's just like barely scraping it. That's a tangent line. So one thing about a tangent line is that a tangent line is actually perpendicular to the radius or the diameter. It doesn't really matter. But these 2 are perpendicular. Okay, remember perpendicular means forms 90-degree angles. Okay, so if this is our picture, it says JL is a radius of circle J. We want to determine whether KL is tangent to circle J. Justify your answer. So what we want to prove, if we want this to be a tangent line, we need to show that KL is perpendicular to JL. We need to see, is L a right angle? So if I assume that L is a right angle, then I've created this nice little triangle here, and in hopes that it's a right triangle. So if we have a right triangle, then there's a couple different things we can use. We could use our trig, which that doesn't really help us for this one because we don't know the angle measurements. But one other thing that we've used lately is Pythagorean theorem. So I could say, well, maybe if this is a right triangle and it follows Pythagorean theorem, then it could be perpendicular and therefore a tangent line. So if this is my, triangle, I would have one side is 15, one side is 8. And then this opposite side of the right angle would be my hypotenuse. Okay? but I don't know all of the other side, okay? I know from here to here is 9, but I'm missing this piece, okay? So that orange piece, I'm not exactly sure what it is, but if I go from J out to the side of the circle, that's a radius. Right? This is just whatever R is, which conveniently we already have labeled is 8. Right here, these two are the same. Okay, so now I can say, well, my hypotenuse, if I have to travel K all the way to J, I can travel 9 plus 8, which is 17. So then my official equation would be 8 squared plus 15 squared. We're going to see if that actually equals 17 squared. So 8 squared would be 64. 15 squared is 225. We're going to see if that equals 17 squared, which is 289. Okay, so 64 plus 225 is 289. Okay, so my a squared plus b squared actually equals my c squared, which means I have a right triangle, and therefore this is a tangent. So yes, KL is tangent to our circle. Okay, our next equation, or our next problem is same sort of idea, but it's a little different. So in this one, we're trying to see is JH tangent. So we're asking ourselves, do we have perpendicular lines? Is J a right angle? Which we know that it is because this time it says that it is a tangent. Okay, this time we're just looking for X. So if we know that we have a right angle, therefore we have a right triangle, we can always use our Pythagorean theorem. Okay, one side would be X, the other side would be 12, so X squared plus 12 squared, and our hypotenuse here would be G to K plus K to H, so this is actually X plus 8 for our hypotenuse. Okay, this is where we might get a little tripped up because of the algebra. So we want all of the hypotenuse to be squared. So we really want X plus 8, that whole quantity, squared. So X squared would just be X squared plus 12 squared, which is 144. And then we have to figure out what X plus 8 squared is. So let's think about it this way. If I write X plus 8 squared, when we square something, we really take the same thing and multiply it by itself. So we're really looking at the problem X plus 8 times X plus 8. So if you remember from Algebra 1, we can't just say, oh, well, X times X is X squared, 8 times 8 is 64, and move on. We actually have to do what we call foiling. So if we do our box method, okay, I'm going to make this a 2 by 2 box because I have 2 terms in the first set of parentheses and 2 terms in the second set of parentheses. And this one, it's the same thing, so it doesn't really matter. I can do my X and my positive 8, X and a positive 8. So what happens is when I fill in my interior boxes, I multiply the terms together. So this box would be X times X, which would be X squared. My box here would be X times 8, which would be 8X. Then I have another 8X right here. And then my last box is 8 times 8, which is 64. So when I combine like terms from my box method, the diagonals will always be like terms. So we can combine those. So this is really X squared plus 16X plus 64. So when I go back over to my purple equation, instead of writing x plus 8 times x plus 8, I figured out, well, this is equal to x squared plus 16x plus 64. So my goal is to get all the x's on one side so that I can solve. So if I subtract x squared from both sides, it actually works out and they cancel on the left. I'm left with 144. They'll actually cancel on the right as well, and I'm left with 16x plus 64. I can subtract 64 from both sides. 144 minus 64 is 80. Divide by 16, and x is 5. Okay, our problem just asked for x, so we are finished. There's another couple examples here, so if we need to do another example in class, I would be happy to do that for you. Okay, we have 2 more things to go over in this video. So this one says that if 2 segments from the same exterior point, so notice these are both starting at B, if we have 2 segments that start at the same point and are tangent to the circle, they are congruent. Okay, so I think sometimes this looks like a bird, like where this is the eye, the center of the circle is the eyeball, and maybe that's the beak. So if we have 2 tangent lines starting at the same point, tangent to the same circle, these 2 pieces are just the same. So if we look, our next picture is almost the same exact thing. Okay, it says AB and CB are tangent to circle D. So they start at B, and then they're tangent to the same circle. So these 2 pieces are congruent to each other. So I could set 2x minus 5 equal to x plus 15. Okay, subtract an x from both sides. And x minus 5 equals 15. Add 5, x equals 20. Oh, and I just needed to find x, so I am finished. If it asked you to find BA or BC, we could just plug it back in. Well, we're done for this one. So the next problem builds off of that same idea, but it adds the idea of perimeter to it, kind of. So a graphic designer is giving directions to create a larger version of this logo. Our goal is to find the perimeter of the whole triangle. So all of these lines are tangents to the same circle G. So if they start at the same point and they're tangent to the same circle, those lines are congruent. So if I start here at the top, AD is tangent as well as AE. Okay, they start at A and they're tangent to the same circle. So this side AE would just be 8 feet. Okay, now we look down here and let's start with B. I'll just go in a circle. So for B, we have this piece from B to E is 7. Well, BE starts at B, tangent to the circle. Well, BF also starts at B, is tangent to the same circle. So these 2 pieces are the same. So from B to F, this is just 7. Which means if we look at segment CB as a whole, if the entire thing is 10, but I've used up 7 of it from F to B, that means I have 3 feet left here to give to CF. So the whole thing was 10. I already gave 7 away. That means I have 3 feet left for CF. Okay, so then for our last vertex, we have 2 tangent lines that both start at C. So CF and CD start at C, are tangent to the same circle. So these 2 tiny pieces here are actually congruent to each other. So C to D would be 3 feet. Okay, now I've labeled everything around. Remember, perimeter, we need to add all of the sides. So if I just start at A and start adding, I would have 8 plus 7 plus 7 plus 3 plus 3 plus 8. And I'm going to put that in my calculator. 8 plus 7 plus 7 plus 3. Oops. Plus 3 plus 3 plus 8. So that gives me 36, and my units would be feet. And that is it for part 1 of step 29.